Okay, so here's class 19, where we are covering, we're going to do differential analysis of fluid flow and CFD. Honestly, today's class is really just going to be differential analysis of fluid flow. And this, we could take a really long time and do a lot of stuff with this. I feel a little guilt about not making more classes on these two topics, but just the way that I decided to divide things up, I spent a lot of time on Bernoulli. And so some of the things we're going to cover are going to be very, very shallow, but we're gonna do our best here. All right, so cartoons that are referential or pertinent to the discussion today. Right here, we're having Wedded demonstrate what's going on in the Navier-Stokes equation. Where on the left-hand side, we have inertial forces, right? This is really F equals ma. This is the ma side of it, mass times acceleration, because we can recognize this as being acceleration, and this is density. So this is really on a per volume basis. And then we can see over here we have pressure difference forces. It's really this pressure difference that drives a lot of flow, right? Well, the flow will move from a high pressure to a low pressure. So here it is. This is just the x direction only. And we can see that, well, we have a pressure difference with respect to a change in position. So that's a pressure differential. We also have gravitational forces. So this is just the density times the acceleration of gravity. And we really don't have gravity in the x direction. So this would probably be zero, but we could have other kinds of body forces, or we might be up in space and for some reason there's a special gravity in the x direction or something. I don't know. And then over on the right-hand side, we have shear forces, viscous forces due to viscosity. Right here, so you can see he's getting all deformed because of the shear that's acting on him. We also talked today a little bit about these lines, these stream lines, but we're going to call them a stream function. And perpendicular to them is this thing called potential, velocity potential function. And this is really an old school attempt to try to come up with equations that describe flow. And if you do any additional work in fluid mechanics beyond this class, you're likely to encounter stream functions and potential functions. And we'll talk about what they are and how they're used, but we won't go too deep into them. This is how they're used often, is we have a bunch of fundamental types of stream functions, and we add them together in what we call superposition. So he's standing in his superposition, and that's how we use those. This is also, we want to be reminded that we have some limitations in certain areas of fluids when we try to do stuff. And one, a very common one, and this is very much true for what we call potential flow. That's what we do when we're using those streams and potential lines. It's we call potential flow problems. You have to have the condition of irrotationality. It has to be irrotational. But that doesn't mean that you can't have a flow that's going in a rotary fashion. It just means that the particles can't be rotating. So that's the idea. On the right-hand side, this is irrotation. I think I have this. Okay, I think actually I have this symbol wrong. Actually, I think it needs to be the other way around. So vorticity is not equal to zero. I guess, yes, I know I have it right. Vorticity is not equal to zero on the left, but vorticity is equal to zero on the right, which makes it irrotational, and therefore we can do potential flow problems. All right, so here's a real-world example from my experience in using computational fluid dynamics. This actually kind of belongs in class 20 because we didn't do any CFD in this class. All the CFD is in class 20, so you could skip ahead to that. But here's something that actually happened. So I worked for a consulting company, a marine engineering consulting company, and there was, while we were on one trip onto the ship, the captain or chief engineer, I don't know which, says to me, we got this other problem. You might smell it. We're having a recirculation of the exhaust gas into the house, and asked asked us, is there anything we could do about it? And we said, well, sure, we could look into it. And I decided that I didn't know enough about CFD to like maybe rent time on a machine. So we went ahead and I think it's really important to know what you don't know, and knew what I didn't know. I also didn't have access to any CFD codes. It wasn't justifiable for our small company to have it. So we hired a contractor to take a look at this, and this is what they came up with. What we found was, and has suspected, it was these vortices that were caused by the bridge wing. And so you can see there's a side view and a top view right here. And is it going to animate? Sure it is. Okay. And you can kind of see like this is particle tracing. You can see that there's like recirculation coming back. All right. So the winds coming off of the bridge wing, we're mixing with the exhaust gas and causing it to come back in. So we were able to demonstrate that what was suspected was happening. Like at certain speeds and certain wind conditions, they were getting exhaust gas to come back. And so one of the proposed solutions was to increase the velocity of the exhaust gas to try to send it up higher so this mixing wouldn't occur. So that was like the idea, and then we were just using pretty much simply Bernoulli onto the exhaust top of the stack and make sort of the nozzle. There was already a nozzle up there, but we made the nozzle. We couldn't make it any higher because it had to have clearance to get underneath the bridges, but we could restrict the nozzle a little bit more. And we also needed to have some amount of quantification of what would be the increase in back pressure because of this, and what kind of effects would it have on the turbochargers, because they don't like back pressure. So we tried this out, and of course we simply could have done this with Bernoulli. But then they reran it, and it looked like this was going to be a safe solution, safe but simple solution. And wouldn't affect the. We also contacted the turbocharger manufacturer and described what we were proposing to do, and they were on board with it. So it was a team effort, and it was a cool result, and we got pretty pictures out of the deal, right? And so a lot of CFD is about pretty pictures. Makes people feel good about solutions to them. And I never did find out whether that cured the problem, but I'm sure hope they did. I'd love to have followed up with that, but I can't say that I did. It would have been a better story if I had. So anyway, we want to try to do some stuff with a CFD, but before we do, we kind of need to go a little bit of historical perspective and find out where it comes from. So on the left-hand side here, this is what we've been doing so far, is to take a control volume and to look and see what are the flows that are coming in and out of it, but really what are the forces on the outside of this control volume. But now we need to go inside and take a look at itty-bitty control volumes and see what's happening to them. So that's really what we're kind of doing in CFD, by the way, is to make a grid out of stuff, and to those individual grid little cubies are really sort of the elements of the little control volumes. So one of the first things that we want to do when we're doing, this down here at the bottom, we're going to use the thing in a second just to sort of demonstrate something. But let's just show them. We'll just show instead of deriving them, show the Navier-Stokes equations. And what we're leaving out, by the way, Navier-Stokes also includes energy equations, but that's usually for doing combined thermal stuff. We're going to go ahead and just limit ourselves to just the continuity equation and the momentum equations, but these are considered the Navier-Stokes equations together. They also include the energy equations, which we're not showing. And the continuity, we just kind of have to accept this for a second. We will demonstrate where that is. Continuity is the conservation of mass. Conservation of mass flow is what's being shown right there, but it doesn't look like it. But we'll show that it is. We have the steady state version of the momentum equation, so you can see that there's no time dependency on this. And you can see that these are partial derivatives with respect to positions, and there's second order partial differential with respect to position. And that makes them nonlinear. And so they're kind of hard to say it, but what we should know is we have 4 equations, and we really have 4 unknowns. So you're going, well, we should be able to solve them. But it's the fact that they're nonlinear second-order partial differential equations that makes it difficult to solve. And so, but the unknowns are the velocities, u, v, and w, and the pressure p. Is what we need to get out of here to be able to solve these equations, but it's not that easy to do. So one thing I want to do is, these later equations are a little harder to look at, but it's fairly easy to show you that the continuity equation is actually right up there. So you take like a little cube, and we say we have the inlets and outlets on all sides, right? So we have an x, y, and z faces on both are either inlet or an outlet, and we divide it in half, right? We say we have a density times the velocity, but then like on the left-hand side, we have, we'll say that the middle is the average. On the left-hand side is 1/2 minus the flow, and then on the right-hand side is 1 plus 1/2 the flow. And if you apply that to our Reynolds transport theorem for volume right there, what you end up seeing is we have on the inlet side we have all the negative ones, and on the outlet side we have all the positive ones. And on the left-hand side we would have well, what you would see is that you would end up getting the results right here is you're going to have, on the left-hand side, we just have the density divided by time times the volume. And you can see all the way through that we have the volume everywhere. So all that volume cancels out. And so what we're left with is the compressible form of the continuity equation, which will also look like this right here in a more compact form if you're going to use the gradient there, the divergent. For a steady flow, a compressible flow right here, you can see the time goes away, and that's nice. But now if you have incompressible flow, the density goes away, and that's what you're left with right there. And you might recall that we used this in, I think, like class 6 in kinematics, to like say that we could show that if this happened to the velocity vector field, the velocity vector field, if that condition held true, then it was in fact incompressible. So that's where it came from, right? Was to do this continuity right here. I promised that we would go through and explain why we did that. So this is the fulfillment of that promise. So by the way, we can also do cylindrical coordinates as part of this Navier-Stokes thing. And I actually do think that I wrote that in my notes somewhere. But let's, okay, right here, by the way, oh, there it is, right there. I said I was going to do it. There she is. There's the cylindrical coordinates version of the Navier-Stokes. And what are the aspects, and what is stopping us from doing, or what is special about the Navier-Stokes? Well, there's only a few things that we could really solve, only a few situations when we apply some limitations and some boundary conditions that make it possible to solve it. And I'll demonstrate them in a series of examples that will hopefully make it a whole lot more sense. So when the fact that we can't solve them, and there's actually been a challenge, I believe there's actually this monetary reward for solutions to the Navier-Stokes equation, and you could get your name named after it and lots of money and fame if you're able to solve something that hasn't been solved yet for using Navier-Stokes. But that's sort of the whole idea behind computational fluid dynamics, is that we can do a little techniques where we can linearize the equations. And then with little linear equations, we can just by way of iteration, by guessing, numerical techniques of guessing and updating and then converging, we can come to solutions of the Navier-Stokes equations through just through number crunching. But it's not necessarily perfect, right? There's a lot more to it than that. But as you'll see in class 20 and in doing the project, it's kind of fun to solve them, but we kind of need to know the background. So I'm going to take a break on this video, and in the next one we're going to do a departure. We're going to try to keep it down to a short session where I describe potential flow and a little bit more of kinematics, fluid kinematics. So that's it, the end of video 1.